Hello, everybody. Welcome to this month's Combustion webinar. I am Peng Zhao from the University of Tennessee. It's my great honor and pleasure to introduce you today's speaker, Professor J. Benziger. Professor Benziger is a professor of chemical engineering at Princeton. He obtained his bachelor in mathematics at Carleton College in 1973 and master in chemistry in Columbia in 1975 and a PhD in chemical engineering from Stanford in 1979. Professor Benziger is an expert in chemical reaction engineering and chemical process technology. His group has developed novel reactor designs for PEM fuel cells that have provided the physical basis to control the dynamic behavior. Professor Benziger's group has also elucidated the coupling of mechanical properties and transport process in polymer electrolytes. Professor Benziger has co-authored over 350 journal papers and holds 7 US patents. He has received the Exxon Award in solid-state chemistry from the Inorganic Chemistry Division of the American Chemical Society and the Purdy Award from American Ceramic Society. He is a fellow of the American Institute of Chemical Engineers. He is on the editorial advisory boards of Industrial Engineering Chemistry and Membranes, and he's a senior editor of the journal Power Sources. So with that, let's welcome Professor Benziger. So the time is yours. Thank you.
Looking at polymer membrane fuel cells as a chemical reactor. Figures of the basic operation of a fuel cell. And in this case, we're going to look at hydrogen fuel cells, where the electrolyte is and so that at the anode, we have oxidation of hydrogen. At the cathode, we have the reduction of oxygen to water. And overall, we are making water. And fuel cells are classified by their electrolyte. And so that many of you have seen solid oxide fuel cells that are used at high temperatures. There have been molten carbonate fuel cells that allow you to work directly with liquid or solid fuels. There's kind of the classic phosphoric acid fuel cells that have been used for energy backup. But the one that is most attractive is the polymer electrolyte fuel cell. Electrolyte. It has efficient electrocatalyst for the anode and the cathode, and it allows you to get high three-phase interfacial contact by spreading the thin polymer film over a porous carbon gas diffusion layer. Basically, very simple shown. We have hydrogen come to the anode where it's oxidized. It makes protons. The protons move across a polymer electrolyte membrane to the cathode. The anode is platinum supported on carbon. The cathode is generally platinum supported on carbon. So everything is symmetric. side chain that comes off that sulfonic acid group. And the sulfonic acid groups are very hydrophilic. The Teflon backbone is hydrophobic, so that the polymer tends to phase segregate into hydrophilic and hydrophobic domains. And so that if you have the right amount of sulfonic acid groups, you can use the hydrophilic sulfonic acid groups as a conductant, and you have the hydrophobic Teflon acts as a mechanical support to hold everything. Cells are of interest is that they operate near ambient conditions. You can run them easily from room temperature up to 80 degrees. They are easy to start up and shut down, and they're tolerant of multiple startup and shutdown. And they have high energy output on both a volume and a weight basis. Electrolyte, so that you're not wasting energy transporting the protons. You want to have an efficient electrocatalyst at the anode and the cathode. And you want to have a three-phase interface with contact between what's called the gas diffusion layer, which is just a porous layer that has the catalyst in it, that you can have the gas diffuse and have a high heterogeneous catalyst interface. Now, most of the effort that's been put into developing fuel cells has been what I'll call the chemical factors. And several years ago, we decided to take a look at the engineering factors. What we just said is, suppose we just take the best chemical materials that are available right now, and let's see if we can make the fuel cell work better with just improving the way in which we engineer the fuel cell. And so what we're looking for is ways to get more efficient mass transport, better ways to distribute the reactants and remove products, and how to operate the fuel cell over a broad range of operating conditions. Chemical reactor. I'm going to start with the idea of showing how a fuel cell looks like a flame. And I'm going to look at what happens when we have multiple phases forming, and looking at how we can operate the PEM fuel cell with dry feeds, and how that we can use this information to simplify the control systems for the fuel cell. So I start with a fuel cell as a simplified chemical reactor. Actually, it's coupled chemical reactors. You have an anode reactor and a cathode reactor. And these reactors are connected by transfers protons. Then you'll have a electric load through which the electrons transport, and so that the protons and the electrons kind of run in parallel paths. Now I've put a dashed line around the anode and the cathode. Line, and then I have some arrows pointing in and out of that. Okay, so the dashed line represents the physical fuel cell. And things that cross the dashed line are the parameters that I can control. So I can control the hydrogen feed or the water feed to the anode. I can control the oxygen feed or the water feed to the cathode. And I can control the rate at which water is removed or the unreacted oxygen is removed. And this simplified chemical reactor has a simple equivalent circuit where I have a battery voltage, which corresponds to the chemical potential difference between the anode and the cathode. I have a load resistance, and I have an internal resistance corresponding to the resistance in the membrane of the fuel cell. Work. They typically have to be hydrated. And this has been one of the major concerns from back in the beginning of polymer membrane fuel cells was how to hydrate the membrane sufficient. And you want to have enough water in the membrane so that the membrane is a good proton conductor. You can think of it as an acid, and you need to have a strong enough or a high enough concentration of acid to carry your current. Now, you also don't want to have too much water, because if you have too much water, you block the hydrogen transport to the catalyst where it is reacted to make the protons. So that what you want to do is find this happy medium where you have just enough water to keep the membrane as conductive, but not too much water to block the reactant flow to the catalyst surface. Fuel cells are equipped with what are called bipolar plates, in which you have to distribute the reactant feed across the area of a fuel cell. And the typical bipolar plates have been using a serpentine flow design. And if you look in commercial literature for what people sell in terms of fuel cells, they almost all use these serpentine plates. And so that you have a serpentine plate on one side that carries the hydrogen for going into out. You have a serpentine plate on the other side. And in between those two serpentine plates, you have a electrode material and a polymer electrolyte, and then another electrode material. Ways to make these serpentine type flow, and I show a few of them here. And one of the efforts, there have been a lot of a lot of effort have gone into trying to find optimal flow patterns in these serpentine plates. And I just show a few of these types of designs in this figure. oxygen, the hydrogen or oxygen concentration, the temperature, how these things affect the rate of reaction in the fuel cell. But the problem we came up with is that we were trying to measure the reaction rates. And if you have a serpentine flow channel, like I show in this figure, you have a variation in the concentrations of reactants and products as you go from the inlet to the outlet of the serpentine flow channel. And so that in order to get the actual kinetics by the serpentine flow channel, I have what we call an integral reactor. And what I would really like to have is a differential reactor where the only gradients I have are transverse between the anode and the cathode. I don't have gradients laterally in the planes of the serpentine flow channel. They're transverse to the membrane. I have what I would call a differential reactor. And that differential reactor allows me to get kinetics directly at the local conditions anywhere along this flow channel. So we came up with the idea of, in order to do these studies, a differential fuel cell. So the differential fuel cell, what we did is we got rid of the flow channels and had an open plenum at both the anode and the cathode. And if we kept the residence time for flow through these open plenums large compared to the gas phase diffusion time, which it scales as L squared over D, then the concentration within the plenum is uniform. You'll have reasonable mixing by diffusion so that you'll have uniform composition in each of these plenums. This means that the reaction rate will be dependent only on the transverse concentration difference, not on any of the lateral concentration difference. We wanted to ask with this differential fuel cell was how much water is necessary for the fuel cell to function, so that we, instead of having a variation in the water concentration as you would have in a serpentine flow, we're looking at the composition being uniform. And so we have a difference in water between the anode and the cathode, but within the layer of the anode or within the layer of the cathode, everything is uniform. I wanted to see, could we operate a fuel cell, a polymer membrane fuel cell, with no water in the feed to keep the membrane hydrated? And so what we did was we took this differential fuel cell and we purposefully changed the amount of water in the membrane to operate the fuel cell with dry feeds. So we pre-injected water into the fuel cell, set the flow rates of hydrogen and oxygen with no additional water, and we ran the fuel cell. And the results shown on here show that if we were below a critical water concentration, in this case it was 0.5 milligrams per square centimeter, you see that over time the current drops off and the fuel cell essentially becomes inoperable. But if we're above a critical water content in the membrane, and this being 1 milligram per square centimeter, we see that over time the current increases until it reaches a steady state. So that this looks just like a flame, if you think about it. It's a flame. If you have enough heat, you get the reaction to go and will run. If you don't have enough heat present, the reaction extinguishes and goes away. And so that the ignition condition being this 1 milligram per square centimeter, this was at a temperature of 80 degrees with flow rates of 5 S at the anode and 2.5 standard cubic centimeters of oxygen at the cathode. If I took that base condition where I had ignition and I increased the load resistance, or I increased the flow rate, or I increased the temperature, all of those would take the ignited condition, and over time, the fuel cell would become extinguished. We even had a student come up with a clever idea of what we called the water match. We had the fuel cell put together, all dried out, running with dry feeds, and there was no current. And then at a given time, we injected water into the fuel cell cathode, and suddenly the current increased rapidly to its steady state. So we saw ignition of the current by adding water at the cathode. We'll point out that you see it, there's an initial very rapid response in a matter of seconds for the fuel cell to ignite, but it ended up taking 3 days to actually get to its final steady state. And that's because there's a time period for the water being produced by the fuel cell to diffuse into the membrane. And so that membrane takes 3 days in order to become equilibrated to the amount of water. So let's see, why do we get ignition in a PEM fuel cell? So you can think of this in the same way as you think of a flame. In a flame, you have the chemical reaction produces heat. The heat accelerates the reaction, and so that you get a feedback loop that leads to ignition. In the fuel cell, we have a balance between water removal and water production. And so that what we find is that at low conditions where we're not producing enough water, then the fuel cell is drying out and it's extinguishing. If we're above a critical amount of water, then the feedback loop causes the membrane to become hydrated and the reaction takes off. And so you end up, in this case, seeing we have 3 steady states, just as you would have in a flame. We have an ignited state at high water activity. We have an extinguished state at low water activity. And you can see there's a blown up section here where they cross each other. And this is the critical steady critical condition for ignition and the multiple steady states. So we then said, well, what happens when we consider ignition with flow channels? So that we can think of the flow channels as being a flow type reactor, as opposed to the stirred tank reactor with the that we were just looking at in the differential case. And so in order to look at what happens as a function of distance along the flow channels, we made a segmented anode where we had 6 segments that allowed us to then look at the current as a function of distance between the flow inlet and the outlet of the fuel cell. Have the material running co-current, the oxygen coming in on the cathode side, hydrogen coming in on the anode side, and we measure the currents in each of these different segments. What we find is that we see the current increases rapidly initially near the outlet at position 6, and then we see a continual ignition as we move toward the front, or to position 1 of the fuel cell. So you get ignition fronts moving from the outlet toward the inlet. And so that we actually set up an experiment where we could do this visually and look at the position along the flow channel. That's from positions 1 to 6. We looked at the current as a function of time. And what we find is if we had co-current feeds, we see initially ignition at the outlet at position 6. And then we see that because water can diffuse in the membrane from the outlet towards the inlet, we see the ignition front moves from the outlet to the inlet. If we put the flows going counter current, then what we find is we get ignition at the center of the fuel cell, and then it spreads out or fans out over time. Showing you at this point is the similarity between an autothermal reactor, a flame, and an auto-humidified polymer membrane fuel cell. Except if you look at in the autothermal reactor, you have a balance of heat generation and heat removal. In the fuel cell, it's a balance of water generation and water removal. In the autothermal, it's a temperature ignition and extinction. In the fuel cell, it's current ignition and extinction. And we get in the autothermal reactor, flame fronts propagate by heat conduction. In the fuel cell, we get current density fronts propagate by water diffusion. Look at now is looking at the effect of water that has and gases that have to move in and out of what we call the gas diffusion layer, or the porous electrode. If you look, I schematically shown the membrane at the bottom is a solid material. Then I have a catalyst layer, which is typically platinum, small nanometer-sized platinum particles supported on a porous carbon material. And then we have a layer of highly porous carbon called a gas diffusion layer. This highly porous gas diffusion layer provides mechanical strength to hold things together. It allows gases to get from the float, those serpentine flow channels. It allows the gas to get from there to the catalyst. And it allows water that is formed to move out of that layer. And it had been assumed when we started some work on this that you had to have large pores in order for the water to get, or you needed large pores for the gas to get from the flow channel down to the catalyst layer. And and if you had small pores, the small pores would be all filled up with liquid water. So that the assumption was that you want a material that has two scales in pore sizes. You want small pores that are going to hold water in, and you wanted large pores that let the gas go in. Out. We built a very simple device where we put the gas diffusion media, this material that has the small and large pores in it, and we put water in back of it with a water reservoir that we could move up and down to change the hydrostatic head of water. And then we looked at what was the flow rate going through this layer. And what we found was that we increased the hydrostatic head, and there was no flow until we got to a critical hydrostatic head. And then we saw water come through. And if you look on the right, this is the water comes through, and it comes through a single point all the time. It just keeps coming through that same point over and over again. And we then realized what was happening was that these porous carbon materials are hydrophilic, they're hydrophobic. And so that the water doesn't want to go through them, and the water looks for the path of least resistance, which is the largest pore. So contrary to what was thought, the water goes through the largest pore, and the gases go through the smallest pore. We could even tell where these pores are. This is the porous carbon material. This is called a porous cloth. It's made by a Japanese company. And if I take this and I backlight it, you can see at the intersection of the fiber bundles, I have large pores, and that's where the water comes out from. And where it's dark is where you have the small pores, and nothing comes through there. And pore sizes will determine how effectively you can get your reactants to the catalyst and how effectively you can get the water out of the material. Set up our flow channel device with putting this porous material in there, and we made it so we could visualize what was going on in the middle of the channel. Realize is you can take these layered materials where you have the membrane in the middle, and you have your anode at one side of it and cathode at the other side. And I can cell so that I could have either the anode facing up or I could have the anode facing down. And so when we did that experiment, if we put the cathode down, anode up, if we had 100% excess stoichiometry in our feed, the fuel cell ran smoothly, very with no fluctuations or anything. If we reduced the stoichiometry, so there was no excess, then what happens is there was no, after we used up the fuel to make water, there was no gas to push the water out. And we started to get large fluctuations in the current. If we put the cathode facing up, we saw that there was not as larger fluctuations, but you saw a significantly large difference in the currents that you could get at the whether you were at excess or no excess. The kind of most interesting case is if we put the fuel cell with the flow channel going into the same direction as gravity, and we had the gas coming in from the bottom, and the liquid water would be normally going downward. What happens is we have water builds up and you get a slug forming. And then after that slug forms, it gets pushed by the gas flow upward. And so that you actually get very regular spatial temporal fluctuations in the current. So that people have tried to use for fuel cells assume a uniform composition and a uniform current density in their fuel cells. What we've actually shown here is that you have you can get very regular spatial temporal oscillations. You can see, we can locate where the water is and where the current density is highest. So where the water is, there's the lowest current density, and where there is no water in slugs in the channel, that we have the highest current. So that we can draw on flooding, we see that liquid water is pushed through the largest pores of this porous carbon or gas diffusion layer, forming droplets. These droplets detach by gravity or shear forces, and they coalesce and form slugs that can be pushed along the channel. The slugs deprive certain areas of the flow channels of reactants and result in local current fluctuations. And stable operation occurs with excess cathode flow and gravity assisting the draining of the liquid. We've developed to look at with dry feeds. Now, there's a real advantage to that in that it makes it much simpler to operate the fuel cell, and we can reduce the balance of plants. We don't need a humidifier to keep the membrane humid. The problems that people were concerned about was that he thought we should only be able to get low current densities, and we can only do this at low temperature. Actually, funding from the NSF, we were told that we didn't know what we were doing. They said, if you look at textbooks, it says extra humidification of reactant gases is essential in PEM fuel cells operated above 60 degrees. This has been confirmed by general experience. So we took our fuel cell, our differential fuel cell, and we put it on in a position such that we had the plenums facing in the direction of gravity. And so that we could then feed material in, the water would be formed, and the water would fall by gravity down to the bottom and be removed. So we call this our self-draining fuel cell. And if we compare this self-draining fuel cell to the typical serpentine fuel cell, you'll notice that the serpentine doesn't matter what direction you move it in, you're at some point going to hit corners where water gets stuck and you can't get it to flow out. Whereas if we take this self-draining system that we proposed, then the liquid water that forms in the gas plenum will fall by gravity to the outlet, and so it will reduce any flooding and allow the fuel cells to operate. Of a fully humidified serpentine flow, and that's this blue, it's the blue triangles. And we compared that to where we had dry feeds. And you can see that when we are below the critical current to sustain steady state ignition, then the humidified fuel cell operates, but the dry feed doesn't. But once you get above the critical ignition point, then it doesn't matter whether you've humidified the feed or not. You get the same current densities. Auto-humidified serpentine. And so that the blue line in the middle, which shows this sudden drop off, is the serpentine flow design operated with humidified feed at 60 degrees. And if we look at then dry feeds, you can see that we've done dry feeds up to 95 degrees, even up to 115 degrees, where we have high currents once we are above the required flow is not a very good one for auto-humidification. If you look at a serpentine flow, it's essentially a parallel flow. And in the parallel flow, if you have too high of a flow rate, then what will happen is you will dry out that part of the fuel cell, and you'll essentially get, over time, a drying front that kills the fuel cell. And if by using the self-draining channelless design, it means that we can operate that with no problem. And so that this shows kind of the current as a function of position at different temperatures and different flow rates in that flow channel design. And you can see that if you're at high flow rates, you get, so here's the high flow rates, you get current near the outlet, but almost none near the inlet. So you only get a little, you get less total integrated current. If you have a lower flow rate, you can see that now you get much more current at near the inlets, and you get more current total output. look at requirements that we can tell when we can operate with dry feeds. The critical point to operate with dry feeds is that you need to have water being produced greater than the water removed by convection. So the water being removed by convection is the flow rate times the partial pressure of the water. And so that we can break this down into, there's a pressure variation, there's a temperature variation, which is the vapor pressure of water, and then there's the flow rate, the stoichiometry. And what you find is that we can operate, there's defined lines here at different pressures, and those different pressures, those defined lines, if we're below the line, if we're to the left of the line, dry operation is feasible. If we're to the right of the line, dry operation is not feasible. And so you can see that we can actually run dry feeds feasibly up to 100 degrees. An important point that to realize is that you don't need the low temperatures to operate with dry feeds. What you do need, and you can see that we can operate at even higher temperatures if we go to higher pressures, is we do need to choose the operating conditions that where we control the vapor pressure of water and the flow rate stoichiometry, so that we always have the water being produced exceeding the water being removed. Got it? We need the net water convection to be less than the water production plus water diffusion. And we can define an effective mixing length, which depends on the flow rates and the size of the flow channels. And this effective length, essentially, if we look at it, defines a Peclet number, which is the ratio of the convective flow through the channel divided by diffusion. And so we can find what the Peclet numbers are for our stirred tank or our differential reactor design versus the serpentine design. Is that the Peclet number for the stirred reactors is less than 1. So the system's well mixed, you get uniform composition, and auto-humidified operation is feasible. If we take the serpentine design, the Peclet numbers is on the order of 100. You have plug flow in the flow channels, you get little axial dispersion, and you have to humidify for the feeds for the fuel cell to operate. Their tank PEM fuel cell is back mixing of the reactants, greatly improves uniformity of the water concentration. It's critical for auto-humidified operation. The flow regime, the scaling is independent of the fuel cell size and the stirred tank design. And orientation of the plenum to permit self-draining of the liquid by gravity reduces the mass transport limitations at high currents. We're proud of ourselves for finding this gravity effect. And we found that shortly after we had published our paper on this, Honda introduced their concept vehicle, which featured vertical flow design that allowed gravity to assist in discharging the water that is produced, resulting in a major improvement in water drainage. So that Honda knew enough how to build the thing, we provided the kind of underlying physics behind it and how it worked. What I want to tell you about is how the fuel cell system how we can improve the control of the fuel cell system to operate with dry feeds. And so that if you think about the way we drive cars normally, we push on the gas pedal to provide more fuel to make the car go faster. But with a fuel cell, if you push more fuel into it, it doesn't matter any because it all depends on how much area you have for the reaction, not how fast you're feeding the fuel in. So we took our self-draining fuel cell and we tried an experiment with it where we took the effluent from the fuel cell and we had to go into water reservoirs so that we could feed hydrogen or oxygen in, and the gases wouldn't just flow through, but they would be held in place by the water reservoirs. And the first thing we found was that as we increased the flow rate with this system, we could get the current we got increased with the hydrogen flow rate. So that this is kind of different than what you normally encounter with the fuel cell. Normally, you see as you increase the flow rate, the current falls off. Here, it increases until it hits a level. And that level corresponds to full utilization of the reactant. And so that what we found is that as here's our fuel cell, if you see it called at the anode, and then there's a water reservoir. And what happens is if we increase the hydrogen feed rate, it puts a higher pressure on to push water down, and it means that more of the anode area is exposed to gas and not water. So we have essentially increased the size of our fuel cell by increasing our flow rate. And if we decrease our flow rate, the water from the reservoir will flow back into the anode, reducing the area of the active fuel cell, which would reduce the current that we get. And so we found that we could have a load following variable power, fixed load impedance fuel cell with 100% fuel utilization, dry feeds, and as you can see in here, it was independent of temperature. So that we've made this very simplified system that becomes much simpler to control and get the desired output. And this was done by an undergraduate senior thesis student, and the National Science Foundation thought very highly of it. She got a patent on this, and it was highlighted on NSF website. So let me conclude with what I've tried to show you tonight. That we've shown you that PEM fuel cells have analogous behavior to classical chemical reactors. They ignite with a critical water content. Ignition fronts propagate due to reaction diffusion coupling, and they develop wet spots compared to exothermic hotspots. And these idealized reactors have led to ways to simplify and improve the PEM fuel cells. We came up with the channelless self-draining design that became auto-humidified to even elevated temperatures, and it allowed us to have simplified dynamic models and simplified control systems. I want to point out that we're still fighting an uphill battle, that the DOE in their plans still want proton conducting membranes that operate at 120 degrees for transportation. And they want membranes that can operate at low relative humidities. Well, what we've shown is we can do that. And it was not by changing the membrane. It was by changing the reactor design. And so that our conclusion that we really is our take-home message is that doesn't, you can make new membranes and things, and yes, they may make a difference, but the big difference, the great science that they're trying to come up with, it cannot compensate for bad engineering. And so it's really, making sure that you design your reactors properly, because making new catalysts, making new membranes, none of those are going to improve if you haven't designed your reactor properly. And with that, I'd like to thank you. And this has been very hard because I get the feedback, but show some of the students that have helped us over time. And with that, I will turn back over to Peng and allow for some questions.